days, but we're going to start solving problems that have exponents in them. I have the strategy written down, and I have a property that's going to be super important to us. Here's what the property says. It's called the one-to-one property, and it's all about, this is going to sound stupid, but it's all about the base. This problem, the thing that's unique about it is they both have the same exact base. So when they have the same base, that's why they consider it one-to-one, because they're the same. When they have the same exact base, you can just ignore the bases and cross them out, and then drop the exponents down and just make that your equation. So we're going to see a couple of different scenarios today. Scenario number one, which is right here on example number one, the bases are already going to be the same. This is the easiest version of the problem that there is. If your bases are already the same, you can eliminate them and just drop the exponents down into your equation and solve that. So we subtract 1 from both sides, and we get x equals 4. There's your answer. If you want, you can check. You can always plug it in. Just make sure 4 plus 1 is 5, and it's 5 up there, so it's perfect. Now take a look at example B. I got to be careful with this because, yes, they're both 6s, and yes, I can cross them both out, but I can't have a problem that's blank. Yes, because this is a 1. Some people mess that up and they put a 0, but it can't be a 0 because if it was a 0, the 6 would have gone away. Well, I guess it could be a 0, but it's probably not going to be. It's just going to be a 1. If it was a 0, then you would have seen 0. Then you add this over. So you get 2x equals 4, and then you just divide by 2. So x equals 2. So if you were to plug it in, 2 times 2 is 4, 4 take away 3 is 1. Checks out. Perfect. The last one, they're both 10s already. Cross them out. So you get 3x equals 2x plus 3. You just subtract 2x from both sides. So you get x equals 3. Now, if you were to plug it in, 2 times 3 is 6. 6 plus 3 is 9. And then on this side, 3 times 3 is 9. So you get 9 equals 9. So it works. So that's the first scenario. The bases are already matching. That's the easiest version of the problem there is. The second scenario is that they don't match. So you can see in this problem right here, this has a 5, and this has a 125. So I'm going to give you the strategy. The strategy for these types of problems is to try to turn the bigger one into the smaller one. So watch this. If I have 5 to the x, could I rewrite 125 as 5 to the something power? What would it be? What would the exponent be? 5 to the 5 is like,
no, that's to the third.
Yeah, it's to the third power. Yeah, so all we do is change one of them. So usually it's going to be the bigger one. Now that they match, we can cross them out, and there's our answer. So if we're looking at example B, which one do we need to change?
4.
Probably the 4, yeah. So could I write 4 as a 2?
Yes.
2 to the what? So it'd be 2 to the second, but don't forget, this already had an x up here, so we have to multiply it with what was already up there.
You just write it as 2x.
Yes. But the reason I did that is because if, let's say this was like x plus 5, I would have to put x plus 5 in parentheses and distribute the 2. And the other side, we can just leave that alone because now it has the 2 already. And now we can just solve it like we did all the other ones. So far the strategies are pretty easy, right? If they already match, just cross them out and solve. If they don't match, change the bigger one. Cross them out and solve. So we have 2x equals x minus 3. So we subtract x from both sides. We get x equals minus 3. So if you plug in minus 3, it's negative 6 up there. Plug in minus 3. Take away 3 is still negative 6. So that's the right answer. Okay, now let's look at this third one. This one's a 9. And this one's a 27. Oh my God, I put a 3. 27. Which one are we supposed to change? 27. So my question to you is, could I write 27 as 9 to the something power?
No.
So 9 to the 1 is 9. 9 to the 2 is already 1 though. So it doesn't work. So
What about 3?
yeah, it is going to be 3. So I'm trying to go over strategy right now with you. So the strategy is change the big one, right? If the big one can't turn into the small one, change them both. So let's think about the small one now. The small one is a 9. We can change that into a 3. Well, not cubed. For this 9, it would be squared times the x. And now the 27 can turn into a 3. That would be 3 cubed. And then this one right here is times the x that's already there.
Is it usually up to x plus 2?
Don't tell me how to live my life. Just kidding. Thank you. This is supposed to be 3 squared, and then this is x plus 2. And now that they both match, cross them out. 2x plus 2 here, and then 3x on the other side. So we're going to have to distribute this one. 2x plus 4 equals 3x. And I'm going to move the 2x over. For me, that makes more sense because it's going to be less work. Our goal here is to try to separate the x's from the numbers. So I have 4 equals x. Then you can always double check, plug it in. So if I put in a 4 right here, and this one would have to be done in the calculator because you're not going to probably know that they're the same. So if I have 9, 4 plus 2 is 6, and then 27 to the 4th, we can check that in the calculator to verify it's the same thing. And it is. I already know it is because I did it earlier. I wasn't sure. So far, so good? So we're solving equations. The bases have to match. If they don't, you have to change them so they do. You can either change the big one into the small one, but if that doesn't work, you have to change both. Okay, and then let's take a look at these last ones. These last ones don't come up very often, but I want to have all bases covered for when we talk about AZ merit stuff. I don't know how fancy they want to get on AZ merit, so these are the fancy ones. Okay. There's a 1/2 as the base, and there's a 4 as the base. Could you change 4 into a 1/2? I don't think so. Probably not. Let's investigate this 1/2 a little more. Is there any way I can rewrite the 1/2 so it's maybe a 2? Because I know 4 can be 2 squared. And this is a stretch. I know this is a stretch because I'm trying to get you guys to remember first semester stuff. So I'm going to assume that you guys just all forgot first semester. Yeah. You guys all agree this is 2 to the 1st power, right? You guys agree with me that I can move this up and change the sign? Remember, usually we don't do that. Usually we try to fix it and then move it down. But we're actually going to go backwards. Stop lying. I swear. You shouldn't swear. So then the 4 is 2 squared. Now we have the matching bases. So we can cross them out. And then you'll have -1x equals 2. So then you just divide by -1. So x equals -2. And if you want to check, if you type 1/2 in the calculator and raise it to the -2nd power, the answer is 4. So let's think about this one right here. I've got the fraction, so I can move that up, right, and turn that into a 64 to the -1. Could I change the 64 into a 4 now? 4 to the what? Yeah, it's just 4 to the 3rd. So that problem is 4 to the 3rd, but it already had the -1 up there, so we're going to have to times that by -1. And then this one is 4 to the x plus 1. Now they match. So guys, what I'm trying to say is anytime you see fractions, there's a chance that your exponent is going to be negative. That's how you would have to manipulate it so that they would look the same. So now the 4's cross out. X plus 1 equals negative 3. Subtract 1 to both sides, and you get x equals negative 4. And that's pretty much all I have to know for today's lesson. But I want to go into these two questions real quick. I want to go back into synthetic division. Synthetic division is supposed to be our shortcut. Do you know when to use synthetic division? Because on this one you can, on the one at the bottom you can't. Yeah, this part right here cannot have exponents and cannot have coefficients. It has to, I call it just a plain x. When this has a 3, now I can't do it anymore. So long division or synthetic division review. For the inside of this thing, we have to have a spot for every exponent, but we don't use any of the letters. We just use the numbers in front. So this is the 2x to the third. This is the 7x squared. This is the minus 6x. And then this is the minus 8. On the outside, we take whatever number was in this parentheses, and we change its sign. We just make it a 4. It's always going to be the opposite. And then there's like this algorithm. An algorithm is kind of like a series of steps that you just repeat over and over. The first step never changes. It always just drops the first one down. The algorithm starts here. So you multiply, and that gives you 8. And you combine, and now that's 15. Then you multiply again, because this is where it's repeating now. 4 times 15 is 60. And you combine. So that's 54. Then you multiply. 216. 216. And then you combine. Was that 208? So once you have your numbers at the bottom there, you just make a small adjustment to the original degree. The degree is the highest exponent. So when you do these synthetic division problems, all you do is lower the degree by 1. So instead of being to the third power, now this is going to be to the second power. So it's 2x squared plus 15x plus 54 plus, the last number is always your remainder. Kind of. 2/8 goes on top though. And then x minus 4 goes on the bottom.
Yeah.
Well, in this though, this is the top and this is the bottom. So that's why it always stays at the bottom. Also, did you guys know we could have figured out the 208 just by plugging in 4? That's called the remainder theorem. The remainder theorem is a shortcut to see if you're going to have a remainder or not. So where did I get the 4 from? It's the number we were going to divide anyways. You just plug it into all of the x's and type it in a calculator, and it would have said 208 anyways. Okay, the long division is also an algorithm, but it's one that people don't like as much. Also, there should be a spot for every exponent. If you don't see an exponent there, there should be a 0. So like if this went from x to the 5 to x to the 3, we would have to put a 0 in the x to the 4 spot. So the algorithm, there's like 3 or 4 steps. You stack them, then you distribute, then you change the signs, and you start all over and keep doing it. So here's my stacking stuff. 12x squared is the first one from the inside on top of the first one from the outside. And you're going to see after we repeat this a few times, it's always going to be over 3x. Now the purpose of this step is to figure out what we need to distribute. It's the answer basically that goes on top. So that's 4x. So step 1 is stack it. So I'm going to put the 4x above its like term. Step 2 is distribute it. So we have to distribute it to this thing. 4x times 3x is 12x squared. And then 4x times -1 is -4x. So step 1 is stack it. Step 2 is distribute it. Step 3 is change the signs. So we're going to change this to a minus, change this to a plus. So these cross out, and now this is 15x minus 5. And now we start the process all over again. So the first one on the inside, if this is still underneath the square root, the 15x, that goes on top, and 3x is always on the bottom. So this is 5. So that's to stack it. So we put plus 5 here. Step 2 is distribute it. So we're going to distribute it and get 15x minus 5. And then step 3 is change the signs. Plus, plus. Oh, just kidding. That one's going to be a minus. So everything crosses out and we get a 0. So if it's a 0, there's no remainder. That means 3x minus 1 is a factor of the larger polynomial. So from time to time, I'm going to throw in some review on the stuff that people didn't like to do or that we didn't do so good at last semester. That way, we're always reviewing for the final exam. And that's pretty much it. So we're on 8.3.